So in the next topic, we want to find a formula to calculate the arc length of a parametric curve. So the idea of arc length, or the length of a path, is that we want to know how long the curve could be if we stretch the curve out like a piece of string. So in order to come up with the arc length of a parametric curve, or any curve for that matter, we're going to follow the approach that we just did for the integral involving the parametric curve. That is, we're going to break this curve down to multiple pieces of like segments, and then evaluate the distance of each like segment. Take the sum of all the distance of the line segments, and then increase the number of the line segments that you want to do the approximations to infinity, and then you have the integral formula. So that's the basic step that we're going to take. So the arc length of a line segment is equal to the distance between the endpoints of the line, and the arc length of a parametric curve is approximately equal to the sum of the distance of the line segment on the arc of the curve. So the parametric curve is of the form x equal to x of t and y equal to y of t for t's between a and b. Here we have to assume that x of t and y of t are differentiable. So that is, we can find derivative for x of t and y of t. Again, to get to the formula, what we do is we partition this curve into multiple line segments. And you want to calculate the length of each line segment. So we're going to calculate the length of each line segment as, so d, which is the distance, d sub I, is equal to the square root of x of t sub I minus x of t sub I minus 1 square plus y of t sub I minus y of t sub I minus 1 square. So this is just the formula of the distance between 2 points. Now this is just the length of one line segment. To approximate the arc length, we're going to add up the length of all the line segments. So add up the length of all the line segments so the arc length is approximately equal to the summations of the square root of x of t sub I minus x of t sub I minus 1 square plus y of t sub I minus y of t sub I minus 1 square for I going from 1 to n. So in this context, n is the number of line segments that you want to use in the approximations. Now you increase the number of sub-intervals you want to partition, or increase the number of line segments that you want to do the approximations to infinity. Doing this, you increase the accuracy of the arc length approximations. So to increase the accuracy of the approximations. We do. So the arc length now becomes equal to the limit as n go to infinity of the summation for I going from 1 to n of this square root value. Now, similar to when we derive the formula of the integral involving parametric curve, you want to have delta t appear in the equations. So what you do here is that you multiply and divide it by delta t square in order later so that later on when you take the limit as n go to infinity of delta x over delta t, you have the derivative of x coming out. And similarly, on this side, you want to multiply and divide it by delta t squared, so that again, when you evaluate the limit or when you take the limit as n go to infinity, y prime appear in the formula. So here we have the limit as n go to infinity of the summation for I going from 1 to n of the square root of delta x sub I of t. So instead of keep writing the difference here, I'm going to use the notations delta x sub I divided by delta t sub I square times delta t sub I, so square. So again, I want to multiply and divide it by delta t sub I plus delta y of t sub I over delta t sub I all together square multiply with delta t sub I square. And as you can see, delta t sub I square is a common factor. You can factor it out and also take the square root of that. Now the limits becomes limit as n go to infinity of summations for I going from 1 to n of the square root of delta x of t sub I divided by delta t sub I square plus delta y of t sub I divided by delta t sub I square. So again here delta t sub I square is a common factor. You can't factor it out and take the square root. So now you have the square root multiplied with delta t sub I only. As you take the limits as n go to infinity, in this term approaching the derivative x prime of t sub I, take the limit, this term will go to y prime of t sub I. And instead of keep writing the limit of the Riemann sum, you're going to turn that into an integral from a to b of the square root of x prime of t square plus y prime of t square. And delta t becomes dt. And this is the formula for the arc length of a parametric curve. Now let's turn to example. So example, you want to find the arc length of the semicircle defined by the equations x of t equal to cosine of t and y of t is equal to 3 sine of t for t is between 0 and pi. Again, the idea of arc length is you want to know how long the curve could be if we stretch out the curve as a piece of string. So here the arc length is calculated using the formula. The integral from a to b of the square root of x prime of t square plus y prime of t square dt for x of t is equal to 3 times cosine of t and y of t is equal to 3 sine of t for t is between 0 and pi, so the integral becomes integral from 0 to pi of square root of, so x prime of t is -3 times sine of t square plus y prime of t is 3 times cosine of t square dt. So you manipulate the integrand a little bit, you get the integral from 0 to pi of the square root of 9 times sine squared of t plus 9 times cosine squared of t dt. And 9 is a common factor, so you factor that out and also take the square root, and you get the integral from 0 to pi of 3 times square root of sine squared of t plus cosine squared of t dt. Sine squared of t plus cosine squared of t is an identity, and that is equal to 1. So therefore, the integral becomes integral from 0 to pi of 3 dt only, and arc length now equal to 3 times t evaluate at 0 and pi, or 3 times pi minus 0, or 3 pi. In this case, the unit is just the unit length. Okay, so that's how you calculate the arc length of a parametric curve. So that's it for this lecture.